There were many unknowns about the universe when scientists planned and designed the Hubble Space Telescope, the most groundbreaking astronomical observatory of its time. One of these unknowns was the existence of stars and galaxies a few 100 million years after the Big Bang, according to Mark McCaffrey, Senior Advisor for Science and Exploration at the European Space Agency ESA. Hey guys, welcome to another exciting video from our channel. Before we go on into further details, subscribe to our channel and hit the bell icon to never miss a video or update from us. Now let's take a look. Even if they were aware of these early stars and galaxies, they lacked the equipment to make Hubble see them. Hubble had a whole lot of top-line goals, many of which were like 20 years old. McCaffrey, a multidisciplinary scientist at NASA's James Webb Space Telescope (JWST) scientific working group stated, "Science had moved on by the time they built it, and science had altered in certain ways. And in the 1980s, shortly before Hubble's 1990 launch, scientists learned that galaxies originated considerably earlier than thought. It became clear that another, much greater space observatory would be required to reach those early stars and galaxies which had lighted up the cosmos after hundreds of thousands of years of darkness following the Big Bang, when the expanding space was solely filled with hydrogen atoms. The technology that would ultimately allow this observatory, now known as the James Webb Space Telescope, formerly known as the Next Generation Space Telescope, to view the mythological first light in the universe, had not yet been built. Infrared detectors, which could catch the feeble light emitted by those early stars and galaxies more than 13 billion light-years distant, were the missing piece of technology. The Hubble Space Telescope was designed to detect visible and ultraviolet light. These early galaxies do emit visible light, but due to their distance, the wavelength of this light is stretched into the infrared region of the electromagnetic spectrum by a process known as redshift. McCaffrey, who was a PhD student at the time at the University of Edinburgh in Scotland, was one of the scientists who pioneered early infrared detectors, a technique that has now culminated into four cutting-edge scientific instruments of the James Webb Space Telescope. In the 1980s, infrared images were taken with a single detector scanning the sky only 1 pixel at a time, McCaffrey explained. "It took an eternity. My PhD thesis focused on the development of the first camera capable of producing 2D infrared pictures. We had 58 times 62 pixels, which was 4,000 times greater than everyone else who only had one." McCaffrey eventually relocated to the United States to work on the Near-Infrared Camera and Multi-Object Spectrometer, NICMOS, the Hubble Space Telescope's first infrared detector installed on its second servicing mission in 1997. NICMOS, which consisted of 3 infrared detectors with 256 by 256 pixels each, provided Hubble with the first glimpse of the infrared universe. Since Hubble's early days, technology has advanced significantly, and the James Webb Space Telescope project has pushed it much farther. JWST's detectors have a resolution of 2000 by 2000 pixels, and we have a plethora of them, McCaffrey explained. "We have a lot more infrared pixels on JWST than Hubble had when it was deployed. So, what with all these pixels, together with all the other components of the mission that make it so groundbreaking, allowed the James Webb Space Telescope to do? The huge mirror of the James Webb Space Telescope will feed the light of stars and galaxies into 4 cutting-edge equipment designed not just to collect photos, but also to investigate the chemical composition of the near and distant universes. This is accomplished through the use of spectroscopy, a method that examines how matter in the cosmos absorbs light. Because various chemical elements absorb light at different wavelengths, scientists will be able to reconstitute the composition of stars, nebulae, galaxies, and planets seen via James Webb's Space Telescope. The James Webb Space Telescope instruments outperform everything previously available by a factor of 10 to 100. Randy Kimball, JWST project scientist for assembly, test, and commissioning at NASA's Goddard Space Flight Center in Greenbelt, Maryland, told Space.com, "There's definitely a 1000 advantage in some of the mid-infrared wavelengths for some sort of observations. These advancements in infrared imaging resolution are important for photographing the furthest regions of the universe, whereas the Hubble Space Telescope or the recently retired infrared telescope Spitzer could only provide a rough estimate of an ancient galaxy's age and chemical composition. Webb will provide precise results," according to Kimball, who previously worked on Hubble Space Telescope instruments such as the Wide Field Camera 3, Hubble's most advanced instrument, which was installed during the final servicing mission in 2009. The Wide Field Camera 3 provided some of the greatest images of the early cosmos. Kimball believes Webb is now poised to eclipse that legacy. The Wide Field Camera 3 runs out of wavelength when it comes to these faraway galaxies, Kimball explained. Some of those detections are dubious, and it will be fascinating to discover which ones are correct. Webb will be able to say precisely when we observe this specific galaxy 250 million years after the Big Bang. According to McCaffrey, Hubble can see up to 13 billion years into the past, and it already detects galaxies that may have created multiple generations of stars by that point in their history. If we're seeing that stuff 500 million years after the Big Bang, it must have been created much earlier by stars we've yet to witness. McCaffrey said, big stars grow and die swiftly in a few million years, so you may have had several generations of enormous stars after 500 million years. While the photos from the James Webb Space Telescope and the Hubble Space Telescope are frequently contrasted, they will show quite distinct features of the cosmos. While Hubble excels at capturing the visible cosmos, Webb's infrared abilities allow the telescope to see past dust and into the center of nebulae, galaxies, and star-forming areas that Hubble cannot see. We know stars are born in locations like the Orion Nebula and other nebulae in the sky, McCaffrey explained. However, optical light is absorbed by dust, so we couldn't look into them. Previous infrared observatories, such as NASA's Spitzer Space Telescope, were far smaller in size than Webb. As a result, they couldn't see as far as Webb, and when they did, they could only get a peek of those star-forming areas at a low resolution. Previously, when we could detect the site of star formation, we'd see numerous objects that were all mixed together, Jones stated. Webb will be able to separate them all. We'd be able to observe the formation of countless stars in clusters that we could previously just detect. While scientists have studied star formation in our own galaxy, the Milky Way, the James Webb Space Telescope will open up star formation hotspots in the universe's furthest reaches. We'll find more distant, more severe galaxies where the environmental circumstances are much different from what we see in the Milky Way, Jones said. Previously, we could only see stars about 8 times the mass of the Sun, but now we should be able to witness the creation of stars about the size of the Sun, which has never been seen before. But it won't be all about faraway places. Webb will also be of interest to scientists who are interested in the Earth's immediate environs. With JWST, we won't be able to gaze inwards towards the Sun, but we'll be able to look outwards, McCaffrey explained. We can observe planets like Mars, Jupiter, Saturn, Uranus, and Neptune, as well as Kuiper Belt. The Kuiper Belt is a ring of comets, asteroids, and other debris that orbit the Sun beyond Neptune's orbit. Because these goods reflect so little light, it's a dreary and chilly environment that's hard to explore. JWST can do incredible spectroscopy on Kuiper Belt objects, McCaffrey said. A big infrared telescope is necessary since these objects are exceedingly cold and do not reflect much light. We know they have ices and other molecules on their surfaces, which we hope to witness. The James Webb Space Telescope was created to revolutionize astronomy. Many of its most important discoveries might come from fields that are still completely unknown today, 10 years from now. What make Hubble and Webb so appealing is because they're both broad-sense observatories, Kimball remarked. They have certain primary research goals, but they have a broad set of options that allow them to create discoveries that aren't in the locations for which the telescopes were planned. Looking at Hubble's top 10 largest hits, you'll see that half of them seem to be for things they knew they were building it for, while the other half were for things no one knew about, such as dark energy and exoplanet research. I hope the same can be said about Webb. And that brings us to the end of the video. We hope you enjoyed watching it. If you did, then drop a like, share and subscribe to our channel for more exciting content. And don't forget to press the bell icon below to always stay updated about our future uploads. See you in the next video.